So this video is just going to be a short little overview of the geometry considerations for a compost pile. What you see here, 3 squares, is kind of the traditional, very common you see in a lot of backyard small setups. There's a lot of other shapes to choose from, and as you add more and more sides, it comes closer and closer to a circle in a two-dimensional view and closer to a sphere in a three-dimensional view. Here we're graphically seeing the ratio of the perimeter of a two-dimensional object compared to the area enclosed by it as you add more and more sides. You can see that ratio keeps going down, down, down. As you add more and more sides, you're getting closer and closer geometrically to a circle, which includes or encloses the maximum amount of area with the least amount of perimeter surface material. And this is a two-dimensional point of view, but you could extrapolate the same concept into a three-dimensional for a sphere. If you're trying to get the most amount of material inside a single object with the least amount of surface containment material, that's a circle or a sphere. That's just an artifact of geometry. So that enclosed area with the least amount of material is not just about construction cost or containment in that sense. It also means that the material in the very center has the most amount of material around it to help it keep warm, both from an insulation point of view and from a generating heat point of view in the winter. It unfortunately also means it has further to go to get oxygen for porosity and air diffusion, unless you're doing active aeration in your pile, and then you don't have that issue. So that can help it stay warm because of the heat generated and staying together by enclosing the most material with the least surface area, because the exposed surface area to the outside cold is where you're losing a lot of your heat. However, it's not always a single object. In a lot of composts, you're doing staging where you have, say, this year, next year, and so forth, the first, the second. And because you have staging in multiple piles, then similar to a honeycomb, there becomes an issue where you have multiple cells coming together to stack in a given area. The reason, one of the benefits of bees not using circles, as you can see here, is the lost area where the circles don't interlock completely, and there ends up being lost unusable space. There are some geometric shapes, as shown here, triangles, squares, and hexagons, which allow you to not lose that space between cells. So one of the nice things about, say, hexagons in particular is that it's gaining some of the benefits. It's better than, so the square is better than the triangle, getting closer to a circle, more area per surface. And then the hexagon is better than the square, and the hexagon still retains the ability to stack multiple cells. For example, if I have roughly 41-inch long sides on a pile that's going to be roughly 5 feet tall, then 3 triangles ends up giving me 561 gallons of space contained within that, and it needs 5 of those side exterior walls and 2 internal dividers to create the 3-bin system. Now, instead of 5 walls, like I did for the triangles, I could still have 3 bins. If I made a hexagon, I use one more 41-inch long, 5-foot tall wall. By having one more wall as a hexagon, I still have my 3 sections, but instead of a total interior contained of 561 gallons for the triangles, as a hexagon, I'm now 1,134 gallons. So more than double from one more wall of material. Now with 2 more 41-inch sides, I can go from the hexagon 6 to 7/8 sides, and now I've reached the traditional 3 squares. And it does increase the volume. I went from the 1,134 gallons of the hexagon to 1,308 gallons of the 3 squares. 2 more sides for more volume. Now, just like we saw going from triangles to hexagon, if we now go from a squares to a 9-sided nonagon, we see again a vast improvement. We went from 1,308 gallons in the 3 squares, traditional size, but if instead we made a 9-sided, one more 41-inch side, we go to 2,700 gallons. It contains vastly more materials, still 3 sections are available inside if we want to split it up that way. For just a little bit more space, we get vastly more enclosed volume. Now, we're also not able to construct this with no external environmental limitations. There are some. The property line, a fence, a road, a building, and so forth can constrict. So if you have, say, a straight fence, if you build a circle there or a hexagon, it's not going to follow the clean line of the fence, which could create empty unused space behind, where you have this interface between a straight line with a property line or a fence or something and this other shape. So sometimes in order to maximize the property geometry, you don't necessarily maximize the container geometry. It just depends on the variables of your particular situation and what you're trying to maximize. In my particular application, I'm aiming for a compost heater, and I want to try to suck up less of my space in my yard to do it. So I'm going to lean more toward things like the hexagon or nonagon that give me the separation between zones, but still keep it in a circular kind of area to help the center stay warm and insulated, things like that, and using the least materials that I have to buy and so forth for the perimeter and to hold it all together and so forth. That's my direction. But like we said, it just depends on the application that you find yourself in. So now if we take a cross-sectional view to start to look at the three-dimensional object, we can see you have a hotter core and then kind of medium and then your outer side. And in air to get through, that's an insulating space. It also, how permeable is it to air? Was the porosity of the material? How well does air get through that? You may need some active air cooling pipes to pull it, to allow sufficient aeration into your pile. But you have a hotter center part, just like if it were a hot chimney or something else, and that hot air rises, so it goes up. You got the warmer air there, and that pulls in more air at the bottom. You get this chimney or stack effect happening. You can have a strong enough, sometimes depending upon the material, the temperature difference between ambient and the core, between the air inlet and the outlet, the porosity of the material, the permeability of the material, et cetera, depending upon your conditions, this passive effect could be large enough to work, but depending upon your conditions, it might not, and you may need to augment with an active system in order to get enough airflow to keep it aerobic. You don't want to go anaerobic, ideally, most people anyway. And it doesn't have to be a round dome like I'm showing here, but you can, the general idea is that you want the heat in the center and it gets the chimney effect, the taller the chimney, so you can get a bigger chimney effect differential and so forth. But one of the issues that small piles have is that during the wintertime, they might not have enough insulation from their material, or they might not be generating enough heat, things like that, in order to keep hot at good composting temperatures. So one thing that is sometimes shown is to take advantage of geothermal heating. It's kind of passive, mostly passive. You basically dig a little, the air inlet is buried a couple of feet underground coming in, so that the cold winter air, as it gets pulled in from that previously mentioned stack effect or chimney effect, as it gets pulled in, it gets heated by that and then rises out. Now, of course, the chimney, the compost pile has to be much, much higher than the air inlet to make sure that it pulls in from that and doesn't reverse. But that's a geometry benefit of going slightly below grade there. It warms that and helps keep that small pile warmer longer with less effort. And it can be passive. And outside the cold winter, geothermal energy also slightly benefits a pile in the hotter parts of the year. And the reason is the thermal siphoning effect. So because the air inlet below ground is colder down there, you go a couple of feet down, it gets colder. That means that air denses, it condenses. So because of that, that pulls in more air from above. So you have a thermal siphon effect. The colder air is pulling in, it's creating its own little part there that's helping pull air in. Slight pressure difference, slight amount of airflow from that. Then the second part is that when you look at the compost pile itself, because the air inlet is now colder than ambient air, the temperature difference that chimney or stack effect sees in the compost pile is even greater, which means that you will have a stronger stack or chimney effect inside the pile to help move airflow. So this approach helps you increase the airflow, of course, try to keep oxygen in the pile. Now, all those mechanisms, whether it's just permeability because it'll go through the pile on its own, or you've added some aeration underneath of it to help this process, sometimes you need more. And so if you're using a fan, but especially large industrial settings, they use fans and so forth to maintain adequate airflow and pressure. You can, even if you're using a fan, take advantage of that geothermal system, especially in the summertime, where it's increasing the airflow volume and would thus decrease the amount of energy spent to move the same volume of air. If you want to put the effort into digging the trench and burying it and adjusting your airflow rates to match the benefit of that and so forth, if you need an active system. You could do passive if all of that is sufficient to get enough airflow. So that's the more three-dimensional, if we want to take that cross-sectional view, part of this geometry of a pile. We want some height. Now, if you have industrial equipment, you can go taller, 8, 12 feet tall or something. For man-sized, I find that getting above 5 feet or 6 feet or so starts to get a little more cumbersome to work with as a person-sized pile. So I'm not an industrial facility, so I'm going to be aiming more for that 5-ish foot range.